Everyone, welcome back. This is Lino speaking. I will guide you through this really intense afternoon. This morning, we saw many interesting talks from malware analysis of Android malware to the possibility to tamper executable file and to reverse engineer firmware in order to find and exploit vulnerabilities. In this afternoon, we'll continue this kind of deeply technical thoughts. But before to start, I just want to provide you a couple of service information. First of all, I will continue to encourage you to use our chat in Slido in order to perform questions to our speaker. And you can find in the general chat a poll, a sort of survey, in order to understand from you guys which was the most interesting talk of this morning. I know that it's quite a difficult choice because all of them were really good, but if you have some preferences, please tell us. Secondly, I know that many of you guys supported us by giving us some donation. That is really, really appreciated, because otherwise we won't be able to provide to you this kind of conferences, as well as the sponsor support. And many of you guys performed the donation in order to reach the t-shirt and the hoodie. Don't worry, we are providing with the expedition of all this kind of gift, and thanks again. So I hope your lunch was good, but even light enough, because the next talk is one of the most hardcore technical talks of NoHead 2020. Alexander Ermolov and Dmitriy Frolov are two security researchers highly specialized in firmware analysis. Their work about low-level security protection are absolutely amazing. And today they will share with us their brand new research about the exploitation of vulnerabilities affecting Intel ACMs. I really think that you need to concentrate a lot in order to follow this kind of amazing talk. So, Alex, Dmitry, the stage is yours.
Hello, everyone. Thank you for being online and attending to this event. My name is Alex, and with the help of my colleague Dmitry, I'm going to deliver this research to you. A few words about ourselves as a start. I have been researching x86 platform security for quite a long time. This work covers subjects like Intel Management Engine, Intel BootGuard, and UEFI biosecurity.
Hello, everyone. My name is Dmitriy Frolov. I'm a security researcher at Digital Security. I specialize on firmware analysis, mostly targeting Intel embedded systems and technologies. For example, UEFI BIOS.
Today, we're going to talk about issues in low-level Intel architecture components, such as microcode, authenticated code models. The previous versions of this talk mostly were about finding and exploiting vulnerabilities in Intel BootGuard and Intel Trusted Execution technology. This time, we would like to cover one of the most protected technologies, I mean from the outer world. There's so little in public about this one, mostly because one of its main components is encrypted and nobody have any idea how it actually works. And we'll start with some basics to make sure most listeners understand what we are talking about. The first part is CPU root of trusts overview. Every modern CPU, Intel CPU, has a processor cores, the bootstrap processor, which starts when powering on. This core begins executing the start instructions in firmware. The application processors, which are started by bootstrap core when ready and needed, an optional graphics core, and integrated memory controller, a level 3 cache shared between the cores, and some input-output logic. Each CPU core has read-only memory containing the CPU microcode, which is programmed while manufacturing the device. And this is our first root of trust. Control unit, after each powering on, loads this microcode into a faster and writable memory called control store. Some sources call it patch RAM. So what is the microcode? Public sources tell us this is a program written in hardware-level instructions to implement higher-level instructions. You can see an x86 MOVES instruction implementation here, for example. Despite the fact the previous example was taken from a science article, this one was taken from the real system, from the real dump, by one of the authors of microcode Red Pill project, who used to dump the microcode from Apollo Lake platform. The thing is, and it is well known for years, the microcode can have bugs, whether these are security issues or not, so it should be updatable. Remember, the original microcode is stored inside the CPU in a non-updatable memory. Hence, the updated version of microcode should be replaced in the control store, patch RAM, every time CPU is powered on. And you can notice such updates are included in system firmware. As you can see, there is a firmware interface table that contains entries pointing to a microcode updates. Please note the updates are CPU model specific. Obviously, the FIT is a part of system firmware stored on SPI flash memory. You can see a common image structure here. There's a pointer at the end of the BIOS region pointing to a FIT. This is how the modern Intel CPU finds and loads microcode update in an automatized way prior to execution of the BIOS. What else do we know about FIT? Well, it had started to be a required element for Intel architecture since introduction of Intel bootguard technology, because it contains entries to point to bootguard components, allowing the CPU to verify the integrity of the BIOS before executing it. Also, like I told before, FIT is used to update the CPU microcode before running any firmware and before starting Intel bootguard. Now let's see what a microcode update binary looks like. It starts with the main headers containing such fields as version, date, CPU model code, a processor signature, checksum, etc. This header is followed by an external header. This is the external extended header structure. Seems like a common Intel signed binary structure also used in Intel CSME firmware, for example. It also has fields like version sizes, processor signature, security version number to deprecate loading the downgraded versions of microcode once the given version is loaded. Also, this header has an RSA public key and signature, allowing the CPU to verify the integrity of the microcode update before loading it. The hash of the public key is hard-coded into the CPU, and based on my observations, can stay the same for a few CPU generations and even for production and pre-production versions of platforms. The microcode update body is unfortunately encrypted, so almost no one actually knows what else the microcode is capable of, besides some startup behavior like microcode updates loading and Intel bootguard. By the way, a few months ago, the decrypted microcode image was dumped from Apollo Lake system on a chip using GTAC through Intel DCI. It could be used as a start to research its contents. I've mentioned this project before. Here are some collection of facts about microcode implementation. Like was told before, it implements CPU structures, it configures the execution logic on the line. That's how bugs like side channel are fixed. Implements some startup behavior like FIT parsing. This is how it can load microcode update from FIT. And it also loads and executes Intel authenticated code models from firmware interface table or not. A few words about ACMs. These are signed and sometimes encrypted Intel code models with the similar structure. With the common Intel binary header. They are loaded into a shared level 3 cache. I guess because of the DRAM is not trusted. By the way, some public sources call it ACRAM. These models executed from there only by BSP bootstrap core. Other cores should be sleeping. They serve as a root of trusts and as an implementation for such technologies like Intel BootGuard, Intel Trusted Execution Technology, Intel BiasGuard, also known as Platform Flash Armoring Technology. Quite interesting note is Intel BiasGuard ACM and microcode updates binary are both encrypted and signed with the same keys. Let's look at the ACM header format. We have already saw something similar today in the microcode header structure. Chipset ID field, which is always 0, build date, security version number, and RSI signature will be key to verify it. Now we can see all CPU roots of trust in a single UEFI BIOS image. Firmware interface table, microcode updates, Intel Trusted Execution ACM, Intel BiasGuard ACM, and Intel BootGuard ACM.
Now let's have a thorough talk about Intel BiasGuard technology. So why do vendors need Intel BiasGuard? The most common SPI flash protection mechanisms, BIOS lock enable and BIOS write protect bits, allow to restrict the capability of rewriting BIOS, so only the code running under system management mode can do that. This approach has an obvious issue. SMM software stack has a lot of code written by different vendors, and its quality is bad sometimes, making SMM vulnerable to privilege escalations from ring 0. That's why Platform Flash Armoring Technology was created, later renamed as Intel BiasGuard. It introduces a small Intel-signed piece of code, BiasGuard ACM, granted with the capability to write to SPI flash memory. If this technology is enabled, all write attempts from any other modes are blocked. There are a few indicators allowing to detect if your PC has Intel BiasGuard. Firstly, the bit 35 in platform info MSR, which indicates if the technology is supported by the hardware. Secondly, the 110 MSR. We will refer to it as BiasGuard control MSR. If bit 1 is set, it means Intel BiasGuard is enabled and write operations to SPI flash memory are only possible through BiasGuard ACM. There is also a log bit to prevent further changes to this register once the configuration is applied. Please note there are a few other BiasGuard related MSRs, and we will talk about them a bit later. However, BiasGuard control is the only one from that list available for operating system. Any attempt to read the others not from SMM will cause machine check exception. By the way, we have noticed that starting from 4th generation as well of Intel CPUs, this MSR cannot be 0 at runtime, because in case BiasGuard is not configured, this register logs itself its settings as 0 bit. Intel BiasGuard support in firmware is implemented in a few modules inside PEI, DXE, SMM phases of UEFI BIOS workflow. However, the most common module is BiasGuard services. This one seems to be developed by Intel and shared between all independent BIOS vendors, IBVs. This module has almost all BiasGuard support logic. However, if you see this module inside the firmware of your PC, this doesn't necessarily mean this technology is working. Only BiasGuard control MSR can tell you if it is enabled or not. The components of BiasGuard technology are BiasGuard ACM, encrypted executable file that implements the technology, BiasGuard platform data table that provides some specific information about the system, includes signed flash area map, important part of the technology that will be discussed later. BiasGuard update package, the container of update data, BiasGuard update package certificate, and BiasGuard log, the component that allows caller to collect data about BiasGuard ACM execution. A part of these components is arranged as an array in SMRAM by BiasGuard services. This array is called BiasGuard directory. In the picture, you can see how BiasGuard directory looks in actual SMRAM dump. BiasGuard directory can be distinguished by its signature BGRD, PFAT on older systems. After you find the signature, you need to add offset 28 in hex. Each element in the BiasGuard directory is a keyword. 7 bytes of each keyword is the address of the specific component, and one last byte is the component's index, meaning the type of the component. You can see these indexes in the left column of the slide. When running, BIOSGuard ACM iterates over this BIOSGuard directory, picking its components. ACM skips empty elements with index FE and stops iterating at element with double F's index. Like was already told, the core of the technology is encrypted BIOSGuard ACM. You can see its structure: external header followed by internal header, and etc. The common header for all Intel ACMs very similar to other Intel signed bindings. Interesting note: corrupting external header will not affect ACM execution, but if we will corrupt internal header or crypto data, the system will freeze after ACM triggering due to verification failure, we suppose. As we mentioned before, all those components are stored inside the BIOSGuard directory. The pointer of BIOSGuard directory should be passed via MSR 115. Once the configuration is prepared, the BIOSGuard ACM can be invoked via the triggering MSR 116 by performing any write operation to it. This can be done only from SMM. You can see this procedure implemented in BIOSGuard services module. And as you can see in the picture, here's BGPDT and BGU, which contain the update data, are passed to the ACM. BGPDT includes signed flash area map. This is a list of SPI flash areas which can be rewritten only with the signed data. BGU with a valid certificate. To protect BGPDT integrity, its hash is stored in MSRs 111 through 114, and once logged, cannot be changed further. Once ACM is involved, it will check BGPDT hash. In case the verification fails, it terminates the operation. So, to override the critical areas of the flash, an attacker needs to modify spam array. But the spam array is a part of BGPDT, and BGPDT is hashed in MSRs and gets validated by ACM. So, attacker's attempt will fail. That's how BIOSGuard is originally conceived. By the way, RS not marked in spam can be rewritten with the help of ACM without any signatures. To better understand the firmware update process, let's look into a MIS BIOSGuard update capsule, for example. It represents some sort of file system. If we look at update capsule's header, we can see this is mostly LCI text that includes some file names and parameters that will be parsed during update process preparations. Each file is managed with BIOSGuard update packages. Each BGU has a header, data section, update data to write on SPI flash in this case, and the BIOSGuard script section right after BGU header. Script section is a very interesting component here. BIOSGuard script is an instrument of communication between BIOSGuard ACM and outer world. It represents a powerful mechanism that can be used to tell ACM what and where should be written on the SPI flash memory with using of arithmetic operations, comparisons, conditional and unconditional jumps, and more. This huge functionality allows caller to write complex programs such as presented on the slide. You can see a disassembled BIOSGuard script of one of the BGUs from a MI capsule from previous slide. BIOSGuard script's functionality allows vendor to implement a program that performs necessary checks right when BIOSGuard ACM is executing, and the process of flashing doesn't need to be interrupted for this. But wait, how did we manage to disassemble it, keeping in mind that the script interpreter is inside the encrypted ACM? Because we got the decrypted ACM.
So, how did we manage to decrypt the ACM? When we ensured ACM is executed from the CPU cache and in the same address space where encrypted ACM is stored, we tried many times to dump it from the cache. We tried probably everything except side channel attacks. We tried relocation of memory mapped EU areas, corrupting input data, and we tried even to steal the ACM while debugging through the Intel DCI, and finally we issued one last attempt, and it failed too. it was really hard to dump the encrypted ACM. Intel did a really a good job on protecting its contents, just to give someone an opportunity to steal it from them. Yes, the non-encrypted ACM version was stored inside Alder Lake package for CMEX along with many other interesting things. We have tried one last idea. Use the recent publication by microcode research team previously mentioned in this talk to create a debugging setup. As you can see, the target Apollo Lake platform supports PFAT, old BIOS name, and the setup allows to access dump to access microcode and to dump it, to modify it, and after we managed to load BIOSGuard ACM for execution on the CPU, we dumped small part of it.
ACM execution consists of two stages. First, hardware initialization includes some initial input-output, MSR operations, and BIOSGuard directory parsing. Finally, we have come face-to-face with security checks that ruined our big hacking plans. The second stage is the script interpreter, where we have found a lot of interesting details about BIOSGuard script. Each BIOSGuard script line has fixed 8-byte length. Instructions include 2-byte opcode number, 1 byte for the first operand, 1 byte for the second operand, and 4 bytes for the third. Method of using these operands can be described by some sort of a mask. For example, if you look at the byte representation of instruction set buffer 1, FF50, you can see that operand 2 is not used. Number of the buffer is passed through the first operand, but long immediate value cannot be passed through the second operand, so the third operand is used instead. So operand 2 can be masked as unused. There are few types of operands used in BIOSGuard script: data buffer, flash buffer, register, and immediate value. If you look at the line 1 of the disassembly, you will see an assignment of immediate value to the register. R1 holds a flash block size now. Then on line 2, a similar assignment is performed, but now it's a flash buffer and immediate value. This kind of operation makes flash 1 to point a flash linear address 0xA50. If this operation was performed on data buffer operand instead, it will point to the given offset of the beginning of this buffer. On line 3, a flash read operation is performed. 1000 bytes from flash at 0xA50 being copied to the temp buffer. On line 4, buffer 1 being compared to the buffer 0. I need to put a remark here. Buffers beginning with number 1 are the temporal buffers that are cleaned and prepared to be used. But buffer 0 is the special one. It points right to the data section of BGU, and it is not writable. So on line 4, a comparison between actual BGU data and temp buffer being performed. On line 5, we're taking a jump if comparison was failed. All in all, these 5 lines are a little program that compares flash block at 0xA50 with BGU data. We can't use CMP instruction in BGU and flash pointer directly because flash data needs to be read into temp buffer first. Unfortunately, we can't cover all of the information about BIOSGuard script during this speech, and there is still interesting stuff about it. And you can play with it yourself. We are proud to announce BIOSGuard script tool that gives you ability to assemble and disassemble BIOSGuard script. It is already available on GitHub.
So this is takeaways from covering the whole untrusted roots research cycle. We saw that the supply chain problems, the disadvantages of security through obscurity model. We saw that the problem in the basic components compromises all technologies, serves as the root of trust, and as we can see a tendency that PC firmware vendors aim to protect code integrity. However, they're still forgetting about other attack vectors. For example, data-only attacks, and we are going to cover this special subject in the next series of talks. So by now, thank you. You can ask questions and we will answer them.
So thank you very much, guys, for your stunning presentation. Very awesome. There are some questions from our audience for you. The first one is, how long did it take for you this research, and how much important was the Intel leakage of last April for your work?
It was about half of the year, probably, and the research, I mean, it took half of the year, and the leakage is not such important because as we showed, there is another way, a technical way to dump the decrypted ACM.
Okay, thank you very much. Actually, personally, I saw that it was much longer research because, you know, the field in which you operate is really tough. So congrats for your for your research. And the second one is about the possibility for malware to exploit the vulnerabilities you found in order to increase persistencies, like Mosaic Regressor recently showed us for UEFI persistency.
Well, usually when BIOS guard is used, it is equipped with boot guard enabled. So the tricks showed here, or any vulnerabilities you find in ACM, in BIOS guard ACM, usually won't allow you to get the persistence without another vulnerability in boot guard technology. In case if you find the vulnerabilities in these two technologies, yes, it will allow you to get the persistence from the operating system, from kernel mode.
Okay, really interesting. Thank you. And I don't think there are other questions in the chat, but I encourage everyone that is attending this conference to make other questions to our speaker, even in chat or even directly. And we will share with you the contacts of the speaker. And thank you very much again, Alexander and Dmitry, for your presentation. It was really interesting. Thank you.
Thank you for accepting up.